Swayam Prabha. Digital India. Educated India.
Today's topic is contingency table and goodness of fit. Now, what is contingency table? Now, when data are tallied into two-way classifications having R rows and C columns, then we say this is a contingency table. That is, the data that we collect can be classified into R rows and C columns. This is called two-way classifications. Sometimes data can be classified in a single row also. That is also possible. We sample many times one population but classify each item with respect to two categories. Now, if I give an example, this will be clear. Now, let us say if a consumer testing service rates denim pants as excellent, superior, and average or poor with regard to comfort and appearance. Now, each denim pant tested will fall into one of the 16 cells of a 4x4 table. So, the question is what? Let us read it again. That there is a consumer testing service or a kind of, let us say, marketing people who want to find out or rate denim pants as into two categories in terms of comfort and appearance, and the ratings would be excellent, superior, average, or poor. So that means there are four ways we can rate them, and we have to rate what? We have to rate two properties. One is comfort, the other one is appearance. Now, if we try to collect data from the customers or from the consumers, you will find that the data are going to lie into 4x4 table. How? Now look at this. We have comfort and we have appearance. So comfort is in the first row, we write it, and appearance we are writing in the first column. And then below comfort I write excellent, superior, average, poor. And appearance, against appearance we are writing excellent, superior, average, poor. Now, if there are denim pants and they are rated in terms of comfort and appearance, these are the 16 cells within which the rating is going to lie. So there is a possibility that some denim pant will be excellent in terms of comfort as well as appearance. So that will come somewhere here. Something could be comfort-wise average and appearance-wise excellent. So that will come here. So like that, if you look at all the possibilities, there are basically 16 different possibilities. And hence we say that here is a table which is 4x4 table, and the data are classified according to their comfort and appearance, and rating is excellent, superior, average, poor. So this is kind of situation may appear. We take another set of data, exact data, where let us say this data is stoppage data of a loom. Now there are several looms, machine number 1, 2, 3, 4, 5, 5 looms are there. So it's not one single stoppage data of looms. So let us say I have 5 looms and we want to are collecting stoppage data over a period of maybe 6 months or 3 months, or could be some time limit must be there. And this is the values I get: 27, 36, 38, 26, 22. Total is 149. Now, what is the question that comes to our mind? Question is, does the data imply that there is significant difference in the stoppage rate? If this question comes to my mind, that whether stoppage rate between the looms are really different from each other, the answer lies in carrying out a hypothesis testing. How do we perform this test? We will say the null hypothesis, no difference in stoppage rate. So alternative hypothesis will be there are differences in stoppage rate. This is obvious and we have already learnt it earlier. Now, if null hypothesis is true, the stoppage rates are not different from each other, then what is the expected stoppage frequency for each of those 5 looms? Total stoppage is 149 and I have 5 looms. So I divided by 5. So this is 29.8. This is the expected value of the stoppage raised. Therefore, if we look at the table now, we write these are the exact values and these are the expected values. That we expect that every loom on an average should stop 29.8 times. So you see, but the observed frequency and expected frequencies are not perfectly matching. There is a difference between them. Total is 149. Total here is also 149. Does the observed frequency differ from the expected frequency or not? So what and we should do? If stoppages occur at random, the variation can be best described by Poisson distribution. Hence, Fe can be thought of a value of Poisson variable. It can be thought of a value of a Poisson variable. If H0 is true, the best estimates of the mean and standard deviation are for a Poisson variable. Mu is Fe, whatever is the expected value of frequency. And sigma, standard deviation, is root over mean for Poisson distribution. So it will be root over Fe. Therefore, provided mu is large, the normal distribution can be used as an approximation of Poisson distribution. And in that case, F0 can be regarded as a values of normal variable with mean and standard deviation as given by equation 1. This is that we can approximate Poisson distribution by normal distribution. Provided what? Mu is large. This is what you have to remember. This mu has to be large. In that case, this assumption will be fairly correct. And if it is a normal distribution, so we know what is normal variable z. Z is going to be F0 minus Fe by root over Fe. If you try to recall z value, z we used to write earlier how? As xi minus x bar by sigma. So exactly same thing we are writing here also. We are describing z variable. So this is my xi, this is x bar, and this one is sigma. So this ratio f0 minus fe by root over ap is a z variable. That is standard normal variable. Now, the null hypothesis is true. If it is true, then expected surface frequency is this much. Oh. And this is all we had already stated. Now what we do, we find out the difference between expected and observed frequency. So this is the difference between these two. This is the difference between 36 minus 29.8. This will give you a figure 6.2. 38 minus 29.8. So these are the differences, f0 minus fe. And then observed frequency and expected frequency, these values are quoted here. Now we find out the value of the z variable, f0 minus fe by root over ap. If I do this, these are the corresponding figures. So we know the values of z. Now sigma z squared follows chi-square distributions. This is also we have discussed earlier, that sum of z variables follows chi-square distributions. So therefore here also this is the basis for significant test, and chi-square value can be used to test the null hypothesis. This was stated earlier in some other previous lectures. If you look back, you'll find that sum of z variables follows chi-square distribution. Therefore, now we can say that z square values, these are the z values. So z square values are given here. They are simply square of this. If you square 0.696, you get a figure 4.8.485. These are all square. Now we have to sum of z square is how much? Here this sum is given 6.336. So this is the value of chi-square. So chi-square sigma z squared is 6.336, which is also the value of chi-square calculated value. Now we have to find out what is this chi-square value from the table. At a level of significance, we have chosen here 0.05. So if we go to the chi-square, this chi-square table with k is how much? 5 minus 1, 4. K is the degree of freedom. K is number of machines. We have 5 looms. So degree of freedom is 5 minus 1, that is 4. So K4, level of significance 0.05. If we look back the chi-square table, we will get this figure from the table 9.448. This figure will be seen. So whenever you are going through the lectures, you must have the table in front of you so that you can immediately check. Now what we find, that chi-square calculated values is this much, and chi-square at the level of 0.5% level of significance, the value is this. So what is this? That means the 6.336, and this is the observed, and this is what we get from the table. So you have to compare which one is more. In the present case, the table value is much greater than the calculated value. And what is the implication of this? It means null hypothesis to be accepted. Conclusion is no difference in the stoppage rate amongst the machine. If we look at the chi-square, the diagram, you will find diagram goes like this. And in the present case, chi-square 4 level of significance 0.5, suppose this value, this is somewhere here. This is how much? We are writing this is chi-square 4 0.05 and this value is 9.448. So here this is 9.448 and the calculated value has come somewhere here, which is 6.336. So it is not going beyond this. So level of significance, that basically means this area is 0.05. So it is below this. It has not crossed. So at the 5% level of significance, the value should have been 9.448 or more. Since the calculated value is less than this, therefore we will conclude that no difference in the stoppage rate between the machines. Hence, null hypothesis is true and we have to accept the null hypothesis. This is how we can do. This particular example also is an example of goodness of fit. That is two sets of data, one based on uniform distribution of stoppage rate is compared. Frequency, because of due to uniform distribution of stoppage rate, is compared with the actual frequencies. And we are trying to check whether there is a difference between them or not. So ultimately we conclude in this case that there is no difference. We take another example of this. In the case of goodness of fit, you can see what is written here, that we compare the observed frequency distribution with the expected or theoretical distributions. So that's what we have done in the previous example. I take another example also. Now here is the following is the distribution of power failure in a mill reported over 300 days. Test at 0.05 level of significance whether the daily number of power failures is a random variable having Poisson distributions with a mean lambda equal to 3.2. So here the mean is already given and the question being raised is, if the lambda value is 3.2 and if it is specified that this is following a Poisson distributions, then whether the rate that we get it here, this frequency distribution that we find it here, does it follow the Poisson distribution with the mean 3.2? So many times we need to check like this. We can also check whether something is following exponential distribution or not. Maybe we have some data available with us, frequency data, where some data already exists and we want to check whether the frequency distribution which is existing with us, does it follow exponential distribution or normal distribution or Poisson distribution or binomial distribution. So whenever this kind of situation arises, that we are trying to compare the existing frequencies that we have obtained with a theoretical distribution. In a way, we can say we are trying to fit a distribution to an existing data set and trying to judge whether this data set that is with us, does it follow normal distribution, does it follow exponential distribution or Poisson distribution. So when such kind of queries are raised, then goodness of fit testing is done. So in the present case, this is a frequency distribution where power failures and corresponding frequencies are stated. We have to check whether it is following Poisson distribution with lambda value, mean value 3.2. So first of all, what I have to do, I have to find out what are the theoretical frequencies. These are the given observed frequencies. What are the theoretical frequencies? So for that, we can find out, in this case, by doing this one, what we are doing, we are trying to find out what is the total number of days and what is the x into f and what is the average. This average is already given here. But if we calculate the average from here, you may get a different figure. It's not that you may exactly get 3.2, you may get some other figure. But the question raises that given lambda value 3.2, is it following the Poisson distribution or not? So what we do? Using this equation, which is already known to you, this is the density function of Poisson distribution, and it says Px will be equal to k is e to the power minus lambda to the power k by factorial k. This is the, we call it the density function of Poisson distribution. Probability that the variable x will take a value k is given by this equation, e to the power minus lambda to the power k by factorial k. Lambda is the mean value. So using this lambda, I am using whatever is given. We calculate the Poisson probabilities. This is what is listed in this particular column. From there, we go to find out what are the exact frequencies now. So if I multiply these probabilities with the frequencies, then if I multiply this with 300, sum of these frequencies, I get a figure close to 12. So 0.04 multiplied by 300, let us say, you will get a figure 12. That means these probabilities should be multiplied by 300 to generate these corresponding expected frequencies. So these probabilities, they have been multiplied by 300, and these are the corresponding actual frequencies that we have found out. So expected frequency is 12.23, actual is 9. Here the expected is 53.43, actual is 42. Then what we do? We go to the next step. That is, we find out the difference between the actual and the expected, f minus fe, and these are the corresponding values we get. Then we find out another value of f minus fe whole squared by fe, because we know that this is the quantity that is when you go for some of them, that becomes my z variable, or that is my chi-square variable. So that's why we calculate this quantity, and the respective values are now given in this particular column as it is from here to there, and then we sum them up, which is 11.46. So if we now look at this, what is chi-square calculated is sigma f minus ap whole square by ap. This is the formula, and that's what we have done, and this 11.46 is the value. Now if we now go to the chi-square table and find out the values, we will find what is the value of k here. I'll count from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be not 8, this will be 9. Chi-square 9.05 will give a value 16.92, which you will get it from the table. So don't get confused. The last figure is 9. So don't think that the degree of freedom is 9 minus 1. Because in this counting, 0 is not getting counted. So actually there are 10 values of x starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 and 0, that makes 10. And hence the value of k, degree of freedom, is going to be 10 minus 1, that is 9. So if we go to the table and find out the chi-square value at degree of freedom 9 and level of significance 0.05, because it is given here 0.05. Someone can say 0.01, someone may say some other value, that is any value that can be chosen. So this value is 16.92, and to calculation we have got a figure 11.46. So we compare between these two, which is more, which is less. Calculated value is less than the value that we get from the table given the level of significance and degree of freedom. Therefore, here also we can say null hypothesis cannot be rejected. Now let us go back to the other situations. Let us say that the stoppage rate of machines is classified into 3 types of stoppage: A type, B type and C type. The 5 machines are there: stoppage due to A, stoppage due to B type, or B type of stoppage, whatever way, let us say A, B, C, the 3 different types of stoppage as are there. And now this data is given here. This is the data you have. Now again the question will come, same questions comes, whether the stoppage rate of the machines are different from each other or not. We find out what is the total. So column total and row total you have to find out first. If you go like this, 14 plus 14 plus 10 plus 12 plus 8, it will give you a figure 58. Similarly, 7 plus 3 plus 8 plus 5 plus 12 will give you 35. 6 plus 9 plus 20 plus 9 plus 2 will 56. You do repeat the same thing column wise also. So this will give you 27, 36, 38, 26, 22. And if I add both of them, these 3 if I add, I get a figure 149. If I add these, also you get a figure 149. So adding the column total values and adding the row total value, they will both should give the same figure. If they are not same, that means something is wrong in the calculation. That is what you have to then redo the calculation again. Okay, now, so 27 is the total number of stoppages of machine 1, which includes A type of stoppage, B type of stoppage, and C type of stoppage. 3 stoppage taken together is giving a figure 27. And this is true for rest of the machines. Now in the case of this also, the null hypothesis, type of stoppage is independent of machine number. Now how do I calculate? First of all, we have to find out what is my expected frequencies of stoppages. If machine 1 behaves identically with others, then expected A type of stoppage of machine 1 will be how many? That will be machine 1, and we are interested about the A type of stoppage. So total A type of stoppage is 58, and total number of stoppage, all types of stoppage, is 149. So what we will do, we will take the ratio of these two, 58 by 149, and multiply it by the total number of stoppage, 27. So if we do this, this will give me a figure 10.51. That is the expected number of stoppage, A type of stoppage of machine 1. Similarly, for the machine 1, if I want to find out B type of stoppage, so we have to, what we have to do? We have to find out, you have go through the row B and find out what is the total here, 35. So we'll take the ratio 35 by 149 and multiply it by 27, and we'll get a figure 6.34. So expected B type of stoppage of machine 1 should be, here we should write 6.34, that is expected value. I can take another, let us say the machine 4. So this machine we have chosen, and we are saying B type of stoppage of machine 4. B type of stoppage of machine 4, actual value is 5. Now what is the expected value? We will go following the same logic. What is the total here? 35 in this row. So 35 by 149, and we will multiply by the column total, which is 26. So 26 into 35 by 149, that gives a value 6.11. So like this, if we follow, we can find out the expected values for all types of stoppages and for all these machines, 5 machines. And if I do this, this table is here. All the figures shown in the blue line are the expected values of stoppages. And you can compare, actual is 8, it is 8.56. Actual is 12, but expected is 5.17. It is expected 2, it is 8.27. So like that, the values have been calculated and they are shown in blue colors. So there are 2 independent deviations for each machine and 4 independent deviations for type of breakages. Now we have to need to know, calculate, next up to this is how many deviations are there. If I show you, the table has been little different looks like, but what we have done, that we have showing the frequencies which is observed or actual. So machine 1 and the type of stoppages A, B, C. Machine 2 stoppages A, B, C. Machine 3 stoppages A, B, C. So we write A2, B2, C2. This 2 indicates machine 2. 3 indicates machine 3. 4 for machine 4. 5 indicates for machine 5. And the corresponding values are given in this table. these are the actual values. And expected values which you have calculated are also shown by these blue figures. Now we find out what is the difference between observed and expected values. They're also shown here. And then we have to go for the square of this divided by expected frequency. We get these figures. So in this, the degrees of freedom, there are 2 independent deviations for each machine and 4 independent deviations for type of breakage. And I think if we observe here, see sum total of observed frequencies in this case for machine 1, actual values are 14, 7 and 6, that makes it 27. The expected values 10.51, 6.34, 10.15. If you add them together, you also get 27. So they should be exactly same. And if I take the deviation and add them together, I get a figure 0. Same thing will happen here also, because if I go for deviations and sum them together, the sum of the deviations will be always equal to 0. And that's why we need to go for squaring. However, f0 minus fe divided by root f e, that is what is the z variable. That's why now, in order to find out the chi-square value, we are going for the square and divided by the expected frequency. Whatever we have done in the previous case, exactly same thing we are doing. There is no difference. In the present case, the independent deviations are 8, and therefore degrees of freedom also becomes 8. So easy way to calculate is degree of freedom is row minus 1 and column minus 1. This is a mechanical way of doing the calculations. So degree of freedom becomes 3 minus 1 into 5 minus 1, and that figure is going to be 8. 2 into 4, which is 8. And if I add all those individual chi-square values, right from here to here, all the values, if we sum them up, we get a figure 27.025. This is the chi-square value calculated value. And now we have to, what is left now? What is the table value of chi-square? That is what is now left out, because we have to compare this quantity with the table value of chi-square at a particular level of significance. So we go for we want to find out what is that value. Now if I try to find out from the table the value of chi-square 8.005 level of significance. The level of significance means the area under the curve beyond this value, this area. This is 0.005. For chi-square, the chi-square curve, if we take this value 0.005 and degree of freedom 8, we get a value which is 21.96, which is quoted in the table. This value and our calculated value is 27.025. So if we plot, see, this is the chi-square distribution. So the table value is shown here, this is here, and the calculated value is shown by this black dot. So one orange dot and one black dot is there. Now you see that the black dot is going beyond the orange dot. That basically means the calculated value is far away from the table value, and therefore we can say that the chances of getting frequencies as shown in the table is very small if null hypothesis is true. and therefore we have to reject the null hypothesis. We will accept the alternative hypothesis because the values indicated by this black dot is far away from here. So and hence we will conclude that H0 cannot be true. Had it come somewhere this side, we could have said that H0 is true. So deciding factor is the table value of chi-square. Based on that, we make a judgment, and in this present case, we therefore reject H0. We cannot accept it. This is wrong. That means there is a difference in the breakage behavior of the 5 looms. They are not really truly, they are not same. But this is not giving you the answer that which machine is different from the other one. For that, we have to actually check the data. This is only saying that the breakage behaviors of the 5 looms are not same. That's all. There is a difference between them. Now, which machine is giving maximum? Where the difference is maximum? And why you need to take corrective actions? They are other questions. No, they are separate questions. So we will not be able to give answer to those questions from here by doing the chi-square test. Chi-square test will only tell you whether a difference between them exists or not. So we conclude, yes, there is a difference. And then if we focus on the actual values of the breakages, then we will see that which particular machine has maximum frequency of breakages and which one is having least. And then wherever the frequencies are high, we have to take some corrective action in order to bring down the frequency of breakages. That is how we can think about applying this particular test. Stoppage pattern is not same. So this kind of exercise you have to do when you are working in industry. It could be different types of looms, of different types of spinning machines, of different types of sewing machines. So or that could be number of machines. In many industries we have same machine more in number. That could be number of that could be 100 cards or 50 cards or 30 cards in a spinning machine, in a spinning department. So similarly, there could be 100 looms or 500 looms depending upon the size of the factory. That could be 1,000 sewing machines in a apparel factory. So, and we try to maintain record about their breakage behavior, so that corrective actions can be taken right in time in terms of maintenance and all, so that overall your efficiency can be improved. So records are maintained, and time to time we have to apply this kind of tests to take or to make decisions which are backed by the scientific principles. That is the principle of statistics in this case. You will see that about half of these chi-square values are contributed by machine number 5. If we look at the chi-square data, this machine has considerable B type of stoppages and fewer C type of stoppages. Hence machine 5 may be an odd machine. So if we look at this chi-square data of machine 5, let us say go back. Machine 5 chi-square data value is how much? 0.04 plus 9 plus 4.9 plus 4, 13.75, 13.77 or 13.81, roughly like this. So this subtotal, if we sorry. If we look at this total value of this figure will be how much? So 0.04 plus 9.02 plus 4.75. That gives you a figure 13.81. How much is this? Only 0.61. This is very, very low. So you can add them and see where the chi-square value is maximum. Obviously, the last case. That means the troubling machine is machine number 5. That is how we conclude. And which type of breakage is more? We have to go back to the original table and see which type of breakage is maximum. So accordingly, we can say the machine 5 is an odd machine, and B type of stoppage and are considerably maybe high, and hence we can identify the machine which needs immediate attention from the point of view of maintenance. So with this this chapter, this discussion is, we are going to close it now. So chi-square test already you have learned earlier. It is only we are applying the chi-square test again for in a different kind of situation. So you see that there are situations where chi-square distribution is going to help us. We can do chi-square test and find out whether behavior of the machines are exactly same or not. So wherever data is given in this particular format, we can always do the necessary calculations and make meaningful conclusions. Okay, with this we close today's discussion.